Hello everyone and welcome to Learning Math. The topic today is the most beautiful equation in mathematics, and there it is. E to the I pi plus 1 equals 0. It's got Euler's E, the irrational number. It's got I is square root of minus 1. It's got the other irrational number pi, that's so famous. It's got 1 and it's got 0. It's got all the important numbers, and that's why it's called the most beautiful equation in mathematics. So we will prove it. The proof uses De Moivre's theorem. It's a very straightforward application of De Moivre's theorem. So what we will really do in this segment is De Moivre's theorem, statement and proof, and then we'll get the most beautiful equation in mathematics as a straightforward corollary. So what's De Moivre's theorem? This is it. Cosine theta plus I sine theta to the n is equal to cosine n theta plus I sine n theta. Now, the proof of De Moivre's theorem uses Taylor series, and I've got a couple of segments on Taylor series that you should definitely watch before you watch this video. So Taylor series, and in particular the Taylor series of e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. We also use the Taylor series of cosine and sine, and you'll see how that comes about. So let's do the proof. So e to the I theta, if we use the Taylor series of e to the x over here with x as I theta, we get 1 plus I theta plus I theta square over 2 factorial plus I theta cube over 3 factorial, and so on. So let's simplify that a bit. And we get 1 plus I theta, and we know that I is square root of minus 1, and I square is equal to minus 1. I cube is equal to minus I, and I to the 4th power equals 1. And then it repeats. All right? All right. So that's 1 plus I theta plus I square theta square over 2 factorial plus I cube theta cube over 3 factorial, and so on. So you have 1 plus I theta, then I square is equal to minus 1, right? So you have minus theta square over 2 factorial. I cube is minus I, so you have minus I cube, minus theta cube, minus I times theta cube over 3 factorial. Then let's write a few more terms. Plus I times theta to the 4th power. I should write the few more terms here. So this would be plus I to the 4th power theta to the 4th power over 4 factorial plus I to the 5th power theta to the 5th power over 5 factorial, and so on, right? So this is plus theta to the 4th power over 4 factorial. And what is I to the 5th power? That's just I plus I theta to the 5th power over 5 factorial, and so on. So now I'm going to group together the odds and the even powers. So this would be 1 minus theta square over 2 factorial plus theta to the 4th power over 4 factorial, and so on. You can write another term here, minus theta to the 6th over 6 factorial, and the other terms, right? I'll factor out the I in the other terms. You have an I over here. See, I, and I. So this would be I times theta minus theta cubed over 3 factorial plus theta to the 5th power over 5 factorial, and so on. Anyone recognize what this expression is over here? This one? That's just cosine theta. Taylor series for cosine theta. And the other one there is sine theta. So you have to really know your Taylor series very well over here. Okay. No, not done. Almost done. So we have e to the I theta is cosine theta. So let's write that down. And I'm going to write it down like this. Cosine theta plus I sine theta is equal to e to the I theta. And then I will raise both sides to n to get e to the I theta raised to n. Then just using exponential rules here, I get e to the I times n theta, right? And then what I'll do is I'll just put my brackets around this n theta like that. So using de Moivre's again, not de Moivre's, this portion here, let's use a different color, using what we just proved, that e to the I theta is equal to cosine theta plus I sine theta, we will get cosine n theta plus I sine n theta. And that's the proof of de Moivre's theorem. Let's tidy it up a bit and put it on the same line. There we go. Okay. So corollary, we get e to the I pi is equal to minus 1. Well, put theta equals pi in de Moivre's result, and we get e to the I pi is equal to cosine n pi plus I sine n pi, right? And cosine n pi is minus 1, and sine n pi will be 0. This is 0. Thus we have e to the I pi plus 1 equals 0. That's it. The most beautiful equation in mathematics is just a straightforward corollary of de Moivre's theorem. And of course, de Moivre's theorem requires Taylor series, so there's some substantial mathematics here. There's another very nice application of de Moivre's theorem. So if we call that corollary 1, we have corollary 2. We can write 1 as cosine 2k pi plus I sine 2k pi, right? And k here is just an integer. So instead of raising 1 to n, let's raise 1 to 1 over n, and we get cosine 2k pi plus I sine 2k pi, raised to 1 over n. And then using De Moivre's theorem again, we have cosine 2k pi over n plus I sine 2k pi over n, right? Whereas De Moivre's theorem, you have cosine theta plus I sine theta to the n comes down, right? Cosine n theta plus I sine n theta. And here we have 1 over n, so that's how you end up with the n in the denominator. And this gives us a wonderful formula for the roots of 1. The nth roots of 1. Let's nth roots of 1. And it's got a nice catchy name, for nth roots of, we want to say the unit, but we say nth roots of unity. So if you want to find the nth roots of unity, you apply this formula. That's because, solving this equation is easy for x squared minus 1 equals 0. It's easy for x cubed minus 1 equals 0. Also easy for x to the 4th power minus 1 equals 0. But it gets harder for higher powers, and that's when you have this wonderful formula for the nth roots of 1. And one thing to note, 0 less than or equal to k less than or equal to n minus 1, because after that it will just repeat. Okay. I guess this corollary doesn't have a statement. If you wanted to put, it just has a proof. So if you wanted to put a statement over here, the statement would be this. 1 to the 1 over n equals cosine 2k pi over n plus I sine 2k pi over n, where 0 less than or equal to k, less than or equal to n minus 1. That's a beautiful formula too. And that's it for today. I will see you in another segment. I'm just tidying up over here.